Hello and welcome to this video about proofs in linear algebra. In this video we'll investigate the proof of a corollary that if a matrix has two identical rows, then its determinant is 0. A corollary is a theorem that is a simple consequence of another theorem that takes a larger amount of space to prove. So we'll prove it simply first and then try to get an intuitive feeling for why it's true. So now to start this proof, we'll set B to be a matrix that's obtained by swapping two identical rows of A. We know from a past theorem that if we swap two rows, then the determinant of the new matrix is minus the determinant of the old matrix. We also know that swapping these rows doesn't change the matrix because the rows are identical. So because these matrices are equal, then their determinants must be equal. So combining these equations gives us this equation, which says that the negative of the determinant of A is equal to the determinant of A. So the only possibility for this equation to be true is if the determinant is 0, so that finishes this proof. So let's look at what is happening and why this is true. We'll look at an example of a 3x3 matrix that has two identical rows. The second and third rows are identical. We'll look at the first permutation of length 3. This is the identity permutation and it doesn't change the input. The output is equal to the input. And these are the numbers that it corresponds to in calculating the determinant of this matrix. It represents the main diagonal. And its parity is 1 because it's already the identity matrix and requires 0 row swaps to get it to be the identity matrix. And since 0 is an even number, then its parity must be 1. This is the part of the sum in calculating the determinant of this matrix. This is a 3x3 matrix, so we can reduce it to have only 3 factors straight away. Then we can substitute the values in for this permutation. These indices point to these entries in the matrix, so that we can substitute in these numbers for these variables. And evaluating this product gives us this number. The next permutation is this, where the last two numbers are swapped. This permutation is a transposition. And these entries in the matrix correspond to this permutation. And the parity of this permutation is -1, because it's a transposition or single swap permutation. So now to calculate this part of the sum for this permutation. There are only 3 rows in this matrix, so we can simplify this expression like this, with only 3 variables in the product. We can evaluate these permutations in the indices. Then we can substitute these entries in the matrix at these locations given by these indices. And then we can evaluate this product to give us this number, and it's the negative of the previous number. If you look carefully, you can see how these numbers double up into an inverse pair, so as to cancel out to be 0. That's because there's a permutation with the opposite parity for what looks like the product with the same numbers. This is why a matrix with two identical rows has a 0 determinant. So now I'll do a calculation of the determinant of a 3x3 matrix, so as to see how all of these permutations double up and cancel out. We'll expand it out using the definition of a determinant. So there's only 3 entries in each product, so we can simplify it a bit more, and we'll just write in the sigma for the dummy variable. So we'll expand it out into about 6 permutations, and we'll observe how the entries are shown for each permutation. I'll just scroll up the screen here. We can substitute in all of the parities for all of the permutations. I'll just scroll the screen up again and I'll circle all of the products in the sum that will cancel each other out. I'll just substitute all of the entries for all of these products. I'll evaluate all of the products. It's clearer now which of these products will cancel. So this determinant will be 0 because the permutations gathered together into opposite pairs that could add together to make 0. So I hope that you've found this video to be helpful and educational. Please click like and subscribe if you did. Feel free to post up any helpful comments and to share this video. And thanks a lot for watching.